Hello. So this is week 5 in my journey to become a machine learning engineer at the Machine Learning Institute. This week was pretty cool. All the weeks are, but this one it was especially cool because we fine tuned, or we were learning to fine tune large language models. Specifically, we worked on fine tuning Llama 2. I found this really exciting because the applications are just, you can really grab these models which are available online and some of them also for commercial use, and you can fine tune them to do a specific task in your that helps you in your business, in your daily life, in whatever you can think of. So I was really excited, and I'm still pretty excited about this and what I can do with after the maybe the course finishes and I have time to think and start innovating and come up with ideas and fine tune these models. So the objective of the week. Oops. I'd like first to actually to take you through the fine tuning. What is fine tuning? Because I found the story and how they got to the technique that we finally used is quite interesting. So I'd like to share that, and then I'll get to it in terms of the data set because what we were told at the course, and which I think was really true. It's all about the data. In this case, in our example, me and my team, my team and I, we used text to SQL dataset from Hugging Face. So basically, we wanted our language model to be given a description, like in plain English, about a query, and then the large language model would predict, or the Llama 2 would predict the SQL command that you would need to use to get your query or the results of your query. Then I'll go through more coding. So we'll look at fine tuning. How does it actually happen in coding? So we're gonna need to look at some PyTorch code or Python code, and then finally, one of the most important things is how we monitor the training and the validations. How we know if our model is learning properly, or yeah. So what other metrics that we're going to be basically monitoring during the training and the validation phase? We're gonna see that on weights and biases. Okay, well, let's get to it. Let's start talking about fine tuning, what it is. So, the fine tuning challenge, when these large language models started, getting developed and out there, we're talking about like billions of parameters. So they get, pre-trained on a massive corpus of text, and then later on, you might want to fine tune these models so that they perform specific tasks. So that's why you would need to fine tune them on that specific task. The model learned generally. Now it needs to learn on a specific task. I'd like to use the comparison as, imagine that the model went through high school, so it now knows a lot of stuff in different topics: history, physics, science, biology, etc. But now it needs to specialize at university, and it needs to learn how to be a chemist or a machine or a mechanical engineer or a civil engineer, etc. So that's what we mean by fine tuning. However, that was very expensive, computationally expensive, because you have to retrain or basically adapt the entire parameters, so 7 billion parameters. So it was a really big bottleneck that the researchers start looking at. How can they reduce this fine tuning time so it's more scalable, and we can start using it to fine tune on any task that we want. So the solutions came in three phases, or maybe three categories. The first one, some researchers looked at prompt modifications. So here we're looking at the input of our model. So some researchers were looking at how adjusting that could actually reduce fine tuning time. Another group or another category of solutions was the adapter methods, and we'll look that into more later. But basically, that's injecting the model with new parameters. So it will maintain its previous parameters, but only the new injected parameters are going to be adapted for the specific task we're trying to teach our model. And finally, the most, I suppose, the technique that made everything, let's say, better compared to the adapter and prompt modifications method is the LoRa, which we're going to also look at later on. But let's start with the prompt modifications. So what's hard and soft prompt tuning? First of all, hard prompt tuning is when you actually, write what the prompt should look like. So it's hard coded, it's fixed. So you tell your model, translate the English sentence. Only the English sentence that you can see here between bracelets gets changed. Then into German is always fixed, and then again the German translation in bracelet changes. So the part that you can see, like translate the English sentence and into German, are hard coded. That's why we call it hard prompt tuning, and that's supposed to um, help the model learn faster. Soft prompt tuning, that's when we're looking at, we're going a bit inside the hood now, and we're creating a new embedding layer, a new layer of parameters that will be concatenated with the input prompt. So the whatever the input of the model is, it gets concatenated, and now we have a new set of layer that would be learned during the training process. So that's what we call soft prompt tuning. And the third kind of tuning is called prefix tuning. So what we saw earlier, soft prompt tuning, in the earlier slide, it happens only once at the beginning of the architecture. So it only happens one at the input side, the input level. In the prefix tuning, this soft prompt tuning concept is taken and introduced into the transformer block. So, as you may know, large language models are transformers, and they have blocks, transformer blocks, where the attention layers are in. So, the idea of prefix tuning is that we take that soft prompt tuning and we add it at the beginning of each transformer block. So now the transformer block receives an input, it concatenates with the soft prompt layer, and then it goes through the other layers or stages of the block, and that gets repeated as many blocks as you have. So if the transformer has 7 blocks, you will get 7 of these soft prompt layers at the beginning of each block. So that's prefix tuning. Now we're moving to the adapter methods. So as if you remember in the initial slide, I showed there were 3 categories. We're now in the second category. So we've left the tuning or the prompt tuning, and we're talking about the adapter method. The adapter method you can see here at the third step, what I explained earlier. So your fine-tuned large language model, these parameters here, they are frozen. Both the pre-trained and the fine-tuned that you can see here, they get frozen, and then you inject a new set of parameters, and you only fine-tune that small set of new parameters. So instead of retraining or fine-tuning the entire parameters, you'd freeze those, add a new set of them, and then just look at fine-tuning these, excuse me, for the specific task that you are trying to teach your model. So let's see in more detail. So again, now we're seeing the transformer blocks again, like we saw earlier. You can see here in red where the adapter layer is injected. So in each transformer block, you would add this adapter just after the fully connected layer. So you can see it's been added here once, and then another once here, and then it goes through layer norm and gets out. And this gets repeated in every block inside your transformer. If you look on more detail, this is zoomed out to see what's inside the adapter. You can see here there's 2 fully connected layers with a nonlinear activation in between. So that's how the adapter looks like. So you can see here, like really, the figure really shows how it gets injected inside the transformer layer twice, and therefore as many blocks as there are. Okay, so we talked about prompt and modification adapter methods. So what are their limitations? Apparently, the adapter introduces inferences latency. So you might ask, well, we just only added a new set of parameters, and we train, if they get trained on GPU, so there's the parallelization. It shouldn't add that much latency, but actually, the way it's been coded, or the way the adapter layer is injected, that it has to be processed sequentially, which means that the power power of the parallelization is not actually used. So that's why injecting this adapter layer actually introduces inference latency. So when the model is in production mode and you want to start making productions, you got like million users trying to use them. That increase in inference time is really, let's say, annoying, or something you want to really reduce or keep to a minimum. In terms of a prefix tuning, what it does, it reduces the model's usable sequence length. So you'd like to have this as large as possible. For example, GPT could like take a story. If you use prefix tuning, you start getting limitations around that. You might be able to just add 1 chapter or 2 chapters. So that apparently has an impact on model quality. So when you're using one of these two, you have a trade-off between efficiency and model quality. And LoRa came in to answer that and to make sure that it reduces efficiency without any impact on model quality. I'll explain briefly LoRa. If you'd like, you could go look at the paper. It's actually really interesting. But basically, the key innovation or addition to the LoRa is that the weight matrix is decomposed into two parts: the weights and the gradients, or the delta W that you can see here. So these are the changes to the weights that happen during the training process. And then what happens is that the gradients or matrices or the adaptations to the weights that would be done through training is decomposed into two low rank matrices, A and B, that you can see in orange there. And the idea, the concept behind why do we how can we represent delta W by two low rank matrices, and what's the use of that? Well, apparently there's this concept of over parameterization. Basically, these large language models have a certain number of parameters, but actually you only need a subset of them to make inferences and to make predictions. So there's a lot of parameters that are not required. And that's why, if you go back to calculus, you know that this intrinsic means that you can represent a matrix with lower rank matrices, and the multiplication of these matrices A and B gives you delta W. But because they are low rank matrices, the computation due to the multiplication of these matrices is much lower and computationally efficient than having to multiply the entire matrix W. So what happens here in this figure is we have an input that arrives into our model. It gets split into two. One that you can see X here. So X gets split into two identical inputs. One gets multiplied by the entire weight matrices W, which is frozen. We do not touch. It will stay there. And then the other copy of X goes to the right here and gets multiplied by the matrix delta W, which is actually made up of a multiplication of matrices A and B. And by having delta W represented by two low rank matrices, the multiplication of X by A and B is much more computationally efficient than if you multiplied X by delta W using the entire shape of the matrix as W. So that's where we're saving a lot. And then the output of these two, so X multiplied by W and X multiplied by A and B, you add them up, you concatenate them or add them up, and then that's what gives you the output of the model. So basically what this is showing is that all the training is happening in A and B. So we've reduced the number of parameters and they are represented by A and B, and only these get trained. The original parameters W that were pre-trained, they are frozen, they stay the same, and you always have access to them, which means that basically once you've trained your model to do a specific task, which means now you have a trained A/B parameters. If you want to revert back to the initial state, matrix W is always there. So you can just cancel A and B, go back to W, and you get the same result that the initial pre-trained large language model was giving. So it's quite interesting. So before we move on to the code, let's just, why was LoRa such a big, progress, and it's now used by everyone who that wants to fine tune large language models? Is first of all, it's much less expensive in terms of hardware required and the storage switching cost, which means basically it reduced the storage requirement uh, or the number of trainable parameters by 10,000 times. So imagine the saving you're doing here. You have 10,000 times less parameters to fine tune compared to the conventional fine tuning. The GPU memory requirement is reduced by 3 times. It does not add any inference latency, and on top of that, it's orthogonal, which means it can be combined with other methods, such as the prefix tuning or other methods that we saw earlier. So it's now widely used, and we're going to see later how we use it also in our code. Okay, so now let's jump into what we've done. So first, as I mentioned, we looked at the dataset. So you can see here the dataset we use from Hugging Face, text to SQL. So you can see here the question. So if you take this example, how many heads of the departments are older than 56? a user would actually input that, and then what the user would expect is the query that they would need to go and get their results. So it would give them back what they expect: select count star from head where age of greater than 56. That's an SQL command that they can go put it to SQL and get the results to their query. And the dataset also has context, which is basically what are the tables that would be required to have an answer like that. So it helps the model a bit more when it has context. So that's how the original dataset is. You can see here three separate columns. What's great about large language models is they don't care about three categories. So what we've done actually, we've taken every row and we've just squished them all together. So now it's very simple. Our data is just a concatenation of both question, answer, and context. And we don't have to really worry about that. We just put them into one training record, and then we can feed now the entire training record into our model and train it, and the inferences actually get predictions. But that's not it. So before we put it in the model, we need to add beginning of sentence token and an end of sentence token. What we mean by token is that now each word is represented by a digit, by a number, but we also want the model to know when the sentence is beginning and when it's ending. And what's a bit interesting this time is the input data and the label data are identical. Previously, I think what we've done in week 4, the input data only had a beginning of sentence token, and the label data only had an end of sentence token. We didn't find these in both, or we didn't find both of these in both input and label data. This time it's even easier. We just add a beginning sentence token and end of sentence token to the input data, and we just copy that and we use this as label data. So it's really easy and straightforward. So at this stage, now we have our data ready to be fed into our model to start fine-tuning, right? Looking at the code, actually, one interesting thing I saw. So this is the training data set that code that actually prepares the data set. One thing that caught my attention is adding the path token. So as you know, when training, you have records with different sizes. And when you want to create batches, that might throw an error because in your batch, let's say we take a batch of 4, one record has 100 elements, the second record has 50. The model doesn't like that. It needs every batch to have the same size. Like in a batch, every record should have the same size. That's how matrices work. So that's why we add this path token. But I noticed we have this option right and left, and I experimented with both, and I felt that the left one is not ideal because the model starts to try to predict actually these tokens, and it might throw the model off. Whereas if I put it at the end, the minute the model recognizes an end of token, it can predict that everything after that is an end of token. So all the padding is end of token. So something to be mindful of, but I thought it might be a better approach than having like padding on the left side. Okay, and then what I did on top of that, just to make things easier for my model, is I added the SQL tokens. So as you know, when using this tokenizer, I think it uses sentence piece, it it uses certain statistical methods to break down your corpus into subwords, basically. So school might become SCH, that's one token, and then OOL, another token. But what we wanted to see here is we want the model to know that to take the tokens for SQL by themselves. So I want the model to keep select as one word because it's going to see that a lot, and it actually helps the model when we tell it this is an entire token. It will identify it easier than if it was two separate tokens as SEL and ECT. So I looked all the list of SQL commands or words in SQL commands, and I put them. And what's good about this code, what it's doing actually, if you see here in terms of subtracting the set of added tokens from what's already inside the tokenizer's vocab list, is it only adds the ones that it doesn't find in the tokenizer vocab list, which is quite handy. So only those tokens that are not already in the vocab keys we would add them to our tokenizer. Cool. In terms of training, one of the changes I wanted to do is the metrics. So I wanted to actually monitor what's happening to precision, recall, F1, and accuracy. And I'll go actually show you the other code. But what I used there, I added the rouge metric and the bleu metric, which I think are quite valuable to evaluate large language models. Okay, cool. Right, let's look at some of the results. These are actually the initial results that we presented on Friday, at the end of the week. But what I'll do later, I'll show you some of the changes I did over the weekend, yesterday actually, which made my model work. So I just show you now where I got to on Friday afternoon that I presented to my colleague. But then I'll also show you the changes that I've done and how the model is performing now. So as you can see, some of the results I'm getting, let's say visually now, you can see that's actually predicting the SQL command very, very well. So this one is almost identical. Well, it is identical, so it got it really right. But it was failing to get the end of sentence. So you see, it was still trying to predict something there. Even here, white space, and then or like new line, and then all of these things. So it's still struggling to learn things that were useless, which I thought wasn't great. Another one here, you can see this one is also doing really, really well. Actually, this one is pretty good example, but that was initially in the training, and then afterwards was getting worse. So as you can see here, you can see immediately that it's actually getting worse. This result was later down the line in the training, and the quality was getting worse. So now instead of average, we're getting count oats. Popular votes from tables was okay. Instead of office, it says year. Instead of percentage, it says year. The number is wrong. So it was actually getting really, really worse. You can see here it's also predicting some commands, even though there's nothing. So I was like, what's going on here? And when I looked at weights and biases, I saw that actually the model gets pretty good quite quickly. So these are the first 500 steps, and each step is 16 training records, a batch of 16. And then it starts going really downhill. So if you see all of these metrics, recall, accuracy, they're all going down. The loss function keeps going down, but even though it seems like it's plateauing here, so maybe there's some overfitting happening, and the model quality is actually degrading as we go. I also tried to fix that with dropout, so I went from 0.005 dropout to 0.01, but actually it didn't seem that it was actually helping at all. So at the end, I thought, okay, there are a few things I'd like to keep doing, which is how can I prevent the model from predicting these padded tokens, or just make it easier for the model to predict something is wrong there. I wanted to help the model focus on learning the answer rather than the question and the context, and look more into how can I identify overfitting and fix that, or for example, stop training if it's starting to overfit. What metrics I can use to evaluate large language models and tell the model, okay, you're overfitting now, just stop. And yeah, doing what hyperparameter tuning I can do to also answer the question of overfitting. So there's a lot of stuff that I wanted to do. I didn't cover all of these over the weekend, but the few changes I made actually got me to a much better place, and the results are actually way better. So I'm going to show you a little bit. I'll go through the code again so you can see what we've done, and then show some of the results. Right, so let's now, we're now at the remote server where we're using GPUs, pretty powerful GPUs to train our models. And we'll start looking at the different sections of the code or the different scripts that we're using to do the entire fine-tuning process. The first one I'd like to go through is the model script. So what you can see here is we're loading, transformer library, which provides the pre-trained models from Hugging Face, as well as the PEFT library, which is the parameter efficient fine-tuning. So this is a custom library that allows us to apply the LoRa method that we saw earlier, layer-wise optimal rank adaptation. And so in the model, what we're doing first is we're choosing the model that we want to get from Hugging Face, which is the LLAMA 2 with 7 billion parameters. The this variable here relates to distributed data parallel setting. So we want our model to be able to split across different GPU cores and be trained in parallel. So we get we fetch our model with these parameters that are related to the quantization, I believe. So that float 16, we would basically each parameter would be represented by a float 16 type, and we're loading it 8-bit, and all of that is very useful to save GPU memory, which is it's a big resource bottleneck. Then what we do is this using the PEFT, we basically want to wrap our model with the PEFT library, which will allow us to use the first to k-bit training, but also the LoRa configuration. And in the LoRa configuration, what's really important to be aware of is this here, the target modules. This will tell you, the llama has probably a lot of transformer blocks with a lot of attention layers. Here we are choosing which attention layers we are going to grab and use in the fine-tuning process. And then finally, we wrap it with the PEFT so that our model now have all of these parameters configured and is ready to be trained with the LoRa method, with the quantization all in place. After that, I think it's important to go through the data set. So now, okay, our model is ready. Now we want to look at the data, and I've explained earlier a lot about these things, but that's the section where we declare or define all of these. The tokenizer. We go grab the data set from Hugging Face. Then we where is yeah. Then here we add all the SQL tokens. It's a function that I've defined, or a method that I've defined later in the code. And then finally we change all of that into the prompt. So remember, we had the question, context, answer. We're mushing all of that together to get our prompt with everything in one single training record. And finally, we tokenize it using the tokenizer that we've also taken from Hugging Face, a tokenizer adapted for the Llama 2 model. So this is the prompt where we get the record and we remove the context question and we mush them all together. The tokenizer, to transform the words into tokens, into digits, and finally adding the tokenizer or the SQL tokens. Yeah, I think once that is done, we get to training now. So as you can see here, we've identified our model. We split our data in terms of training and validation. The collator here function is the one that is responsible of padding each training record when we get them in batch. So if you remember, I explained something around each batch has to have the same amount of same size. So if we have training records with different size, the collator will automatically pad them with zeros or with whatever token we've chosen. And if you remember, the right option means that it will pad them to the right, not to the left. This is important. We resize our token. This is here we're resizing our model or the token embeddings in our model to fit the new vocab size that we have after adding the SQL tokens. And then we define the trainer in our transformer with all these configurations regarding to what other data set, which the collator here, the tokenizer, how many batches we want, or the size of each batch, how many epochs to train, the learning rate, the float precision 16, a bunch of variables that are required, how many, the total limits here. So basically, what's happening here is every 100 steps the model is being saved, but it only will keep 5 folders. So every 5 steps, whatever was saved before that is going to be lost, and we're only keeping 5 folders because they can get really, the volume of each one is about a few gigabytes. So you want to keep a limit on that. The compute metric, this is the function I talked about, and as I mentioned earlier, I added the Sacre Bleu and the Rouge, which I think are more valid for large language models. And then, I print a few examples to see actual text that is being generated, just to visually also evaluate that. Then we tell the trainer to take the compute metrics function as the one we've defined here, and then we start the training process. Right, so this happens in weights and biases. So First, maybe let's look visually at some of the outcomes. So see here that our model is training. If I take here, you can see that it's struggling. So this is the generated text, and this is the input text here. So you can see in terms of that first prompt, the hard prompt, it's getting it right. So it's predicting it exactly the same. It struggles with the question. It's still struggling with the question even after this time. So it's not getting it right. The question should be, what is the total number of decile for the Redwood School locality? But it's saying pointile of the Air House School Board. So struggling. But it's getting the context pretty much right. Only the number is wrong. So here's the 34. Here we're saying 79. However, the SQL command is it's getting it right. So select count is it's identical actually. So that's pretty good, and really that's what we're interested in. Oops, now it's a new. So if we go, let's go back. Yeah. So again, you can see here the it's getting it really good. It's doing very well in predicting the SQL, and that's really what we're interested in. The other parts of it, we're going to give it during inference, so I don't really want my model to be able to predict any of this. What I want is to get all of this right, both the SQL command and the end of sentence token. All of these represent the end of sentence token, which is it's getting it right, but actually not quite yet. So you can see here it correctly predicted end of sentence token, but then it started predicting beginning of sentence token. So yeah, that's something I still want to look at because I want my model to ignore all of this and not spend resources trying to predict any of these because they're insignificant. Once I uh, correctly identify my end of sentence token, I want my model to just stop trying and just ignore everything else. So one thing I need to look at maybe later down the line. Yeah, as you can see in most of the examples, it's really failing. Um, I mean, it's getting the end of sentence token, which is great, but yeah, it's still struggling with predicting that everything else should be end of sentence token. Right. Okay. So that's like a visual inspection. It seems like yeah, it's getting the SQL commands pretty good. That's another example. Yeah, I can see that it's really good. Let's look at some of the metrics. Okay, so what you're looking at here is what I've done. So here we're looking at the four Rouge parameters: Rouge one, Rouge two, Rouge L, and Rouge L sum. You can look into this each one of these, but they're one I think is for unigrams, bigrams, sequence. You know how the longest sequence in the predicted sentence compared to the input one. But you can see the comparison. Maybe if I do that a bit more, you've got two runs here. If you remember, there's the orange one is the one with a dropout layer of 0.01, whereas the green one is with 0.005. And it seems in terms of the rouge, they're quite similar and they're all going up. They're pretty close. However, if we take the blue metric, it seems that the dropout of 0.01 is actually better. Um, yeah, yeah, it seems like there is some overfitting, and actually increasing the dropout might make the results better. We've got the accuracy, recall. Ah, interesting. Look at the loss function. Yeah, so it seems that again, with the 0.01 dropout, see the loss function is nice and smooth and keeps going down. Whereas it seems like with 0.05, I feel like it's getting close to a plateau, which could be an index of overfitting, which is interesting. Okay, another something that is a bit strange, which I don't understand. You can see here the rouge metric is between 0.66 and 0.74, and actually the rouge metric these are showing the F1. So each the R1, the R2, the RL, and the RL sum, they're also showing F1, which is sort of an average of the precision and recall. However, when I take them individually, you can see that the F1 has a different scale from 0.021 to. That's something I still don't understand, and I still would like to look more into. Yeah, similar for recall. I don't get these metrics, these y scales. So I need generally to have a better understanding of how do we evaluate large language models dive really deeper into the evaluation metrics. You know, how can I tell my mother like if this is offer fitting? I'd like to know that and stop. But I'm not sure. I still yeah, that's something I'd like to really look into in the upcoming days or weeks. Cool. So that's measuring or monitoring training and validation accuracy. If you on weights and biases. And once we're done, we can actually grab the eval script here, which basically takes the what we this is the checkpoint path. So if we save the model at step 4900, it would be saved here. We can grab it, load our model, and then start making our own predictions. So you can see here that I've just given the model the template of the prompt, a question, and the context, and what I expect it to generate is the actual response. So that's what I meant earlier, is that the model doesn't really need to correctly predict any of these because we will be giving them that in the inference stage. All I wanted to do is to get the response right. So once the training is done, I'll grab my model, and this eval script allows me to make predictions. One thing I'd like to point out that took us really a lot of time to figure out is these two functions here. This is how you would actually load the model, the trained model. We tried this previous command, but it seems like it's not working. So we spent a lot of time actually, googling and asking ChatGPT and finding in other sources what's actually the best way to load a model or train model using the PEFT library, and we finally managed to find that. So yeah, it's really super exciting. It's amazing to see being able to fine tune a large language model to do a task like that, which is not straightforward. And Yeah, I can't wait to do that on other data sets, which maybe would be more interesting for me. Like one thing I was thinking of what I'd like to do is fine tune a large language model to respond to you like Marcus Aurelius would. I'm fascinated by the Marcus Aurelius character, as a Stoic and presumably one of the only philosopher king that ever existed. I read a few of his books, and yeah, I find a lot of wisdom and comfort reading some of his reflections on his life in his diaries, or the published diaries, which are called meditation. So I would like to actually fine tune a llama or a large language model where I can ask it questions and it would respond to me like Marcus Aurelius would. So yeah, watch the space. Hopefully, I'll get some time to prepare the data set, because I'll need to provide it like a question and answer data set. And if I do, I'll also make a small video, and maybe actually, if I can, I'll maybe do like a small web app, and people can go and have a chat with Marcus Aurelius. So yeah, that's it for this week. It's been really really cool, and I've enjoyed it a lot. Oops, that's another evaluation step. It's been really cool. I've really enjoyed it, and I've learned a lot. And I'm really super excited of what I'll be able to do with large language models. So, yeah, thank you for watching. And if you have any questions, any comments, any feedback, I'd very much appreciate it. Please reach out, whether it's in the comments or if you want to, find me on LinkedIn. My name is Bashar Kabalan. You can find me there, Bash. So yeah, and hopefully I'll add some links in the comment section, description section. Thank you again, and see you next time. Bye.